We're going to start with learning some rules for differentiation. Differentiation is the verb form of finding derivatives. So I'll say differentiate. That means to find the derivative of something. So we're going to learn some rules to help us out. We're going to talk about the power rule. We're going to talk about what to do with when powers are negative, how that works. We're going to talk about finding a first, second, and third derivative. And then we're going to review tangent and normal lines. All right, here is rule 1. If f is a function with constant value c, all right, use your arms to show me constant value c function. Like 5 or like 10. This, right? It's just a horizontal line. That is a constant. If I ask you for the derivative of that, what am I asking you for? The slope. What is the slope for every constant function? 0. There you go. You have your first rule. You never have to prove that. Okay? The derivative of 7 is 0. The derivative of 1,000,000 is 0. The derivative of pi is 0. The derivative of e is 0. Why? Because all of those are constants. There may be irrational constants, but they're still constants. All right, rule number 2. If you have a function where you have, typo, this should be an x, and you have cx, that means a constant times x. Use your arms to show me the graph of a constant times x. Some of you are going this way, some of you are going this way, okay? A constant times x, it could be a positive constant, it could be a negative constant. What is the derivative? If I'm asking you for the derivative, what am I asking you for? The slope. Do you need calculus for that?
No.
No. What is the slope of either one of these? Whatever c is, whatever the constant is. So the derivative of that is c. You don't need calculus for that rule. Okay, you only need calculus when we get to powers. Because powers make functions do what? Okay, well, yeah, and they're not straight anymore. What does it make them do? It makes them curve. And as soon as you have a curved function, you need calculus. All right, we've proved how Leibniz and Newton came up with curved functions. We can simplify the two of them. We can take all of Newton's work, we can take all of Leibniz's work, and we can summarize that in one rule together. And the rule is the following. If you have a power, starting with the power of 2, then the derivative can be formed by this rule. The n gets moved to the front. So it becomes n times x. And the power gets dropped down by a value of 1 from wherever it is. So the new power is n minus 1. So the old power moves to the front, and the new power is 1 less than what you started with. So if you start with something that is a cube power, its derivative will be 1 less. It'll be a square power. If you start with a problem that's a 10 power, its derivative will be a 9 power. If you start with a power that is a 5/4, its derivative will be 1 less than 5/4. So you have to be good at subtracting fractions. So its derivative will be 1/4. Okay, it's down by 1. That is the rule. That can be proved by Leibniz and Newton. They both proved it separately from each other, but they can be summarized in that one rule. All right, so if we can work through these quickly, we can come up with what their derivatives are. All right, so if we have 5x to the 4th, the derivative prime value is, I move the 4 to the front of 5x, so the old power moves to the front, and the new power becomes 3, so the total answer would be 20x to the 3rd. That is called the derivative. That derivative would represent the value of the slope at any point on that curve that you would desire to find. You can zip to that point. I want to know what the slope is going to be at -1, and so you plug -1 into the derivative and find out that the slope will be -20. All right, g of x, the next one. The rule is called the power rule, so it only works if the function has a power on it. The way g of x is written, it's not written with a power, so you would have to rewrite that so that this has a power, and you would rewrite that as x to the half. Once it's written in power form, then you can use the power rule. So the g prime would say that power, that old power, moves to the front, so now I have half in front of x, and the new power would be 1 less than the power I started with, and 1 less would be -1/2. You would never want to leave your answer with a negative in its power. You want to give me the equivalent fraction for that. And so that would mean I have a numerator and a denominator. So my numerator is 1, my denominator is 2, and then the rest of my denominator is the square root of x. That's x to the half power. Okay, so you would always want to finish that. Don't ever leave me with a negative exponent. You don't have to rationalize your denominators, but you do need to make them so they're not negative. All right, the next one, h of x. Again, the power rule only works if it's written in power form, and 1 over x to the third is not written in power form. The power form would be x to the -3. So you have to turn it into a negative power in order to apply the rule. And then once you apply the rule, you take it back out of the negative form. So into a negative form and then out. So then my derivative would be the -3 moves in front of the x. And what will the new power be if I'm going 1 less than what I started with? -4. And then I want to put that back into a fraction form, which means the numerator is the -3 and the denominator is x to the 4th. Okay, are there any questions so far about, bless you, the power rule? Okay. Then we have the sum and difference rule. And the sum and difference rule says that if you have a function that has a bunch of parts in it that are added and subtracted to each other, then you just apply the rule individually to each part. So you would apply the derivative rule to the u part, and then you would separately apply the derivative rule to the v part. So they're all done separately from each other. This only works for addition and subtraction. It doesn't work for multiplication. There's a whole nother rule for that we'll learn, not today. Yeah?
Is that the chain rules?
No, that is different. Okay? That's coming also. So here's an example of a function that has a subtraction in it. And so I will be applying the derivative rules separately to the part that's the cubic part and the part that's the squared part. But first of all, let's look at what we're asking for. We are asked to find the tangent line. So as I find a tangent line, I'm going to be finding y minus y1 equals m times x minus x1. But what things do I need to find a tangent line? What two things? Point and slope. So we'll start with point. And the point is going to be the value of 1 for x and the value of 3 for y. So I got that by just plugging in the number 1 into the given function. My slope is going to be my derivative. My derivative is going to be the power rule applied to each piece. So my derivative would be, if I look at that, it's a 3 power, so 3 would move to the front of 6x, and the new power would be squared, so that would be 3 times 6x. And then minus, and then the 2 gets moved in front of the 3x, and the new power is simply 1. So I look at that and I say, oh, that's 18x squared minus 6x. That is called my derivative. to find the slope value, I need to plug the number 1 into that as well. And so that would be 18 times 1 squared minus 6 times 1. In other words, I get 12. So my tangent line would take those two things. It would take the point, and now it would take the value of the slope. So my tangent line would be y minus 3 equals 12 times x minus 1. Okay, any questions about that? Yeah, Giselle. So the rule here is to take the 3 and move it to the front, and then to decrease that power down by 1 to 1 left. So it changed from a 3 to a 2. Okay, here, find the equation of a tangent line to the curve y equals 1 over x at the point. So again, we find the equation for a tangent line, which means we need a point and we need a slope. Now the point was given to us as 1, 1. The slope will be the derivative. The derivative is going to be the power rule, but my function is not written as a power right now. It's written as a hyperbola. So I need to change this function, which is written as a hyperbola, into a function that would be written as a power. And the power is going to be x to the negative 1 power. Once it's written as a power, you can use the power rule, but you can't use the power rule until you've written it as a power. So then I can move the negative 1 to the front of x, and I can lower the value to negative 2. Okay, I'm lowering it. It goes smaller than what it is. I subtract a 1. And then I want to turn that back into a numerator-denominator fraction. So the numerator would be negative 1. The denominator will be x squared. Then to find the slope, I plug the value of 1 into that. So negative 1 over 1 squared, or negative 1. So my tangent line will be y minus 1 equals a slope value of negative 1 and x minus 1. So that's my tangent line. If I wanted to make it a normal line, what's the only thing I have to change? I only have to change the slope in the middle. If I wanted to make this a normal line, I would take the slope in the middle and make it the reciprocal with the opposite sign. So that would be positive 1. Okay, does the curve have any horizontal tangents? And if so, where do they occur? Well, I can see that it has horizontal tangents. A horizontal tangent is going to be happening right here, and right here. Okay, those are 3 horizontal tangents. But how can I find where they're at? Well, a horizontal tangent means that it has a certain slope value right there at that minute. And the slope value is 0. And in fact, it has the slope value 3 times of 0. I'm not plugging 0 in. I'm saying that the slope is 0, and synonymous to slope would mean the derivative is 0. So we know that the slope, which is equal to the derivative, must be equal to 0. And so I'm going to find my derivative and set it equal to the value 0. I'm not going to plug 0 in. I'm going to set it equal to the value of 0 to find this horizontal tangent. So my derivative, I can do each piece because each piece has a power. So I'll start with x to the 4th. I'll move the 4x in the front of the x, and I'll decrease that to a 3. So that's the first derivative. Then I'll subtract, and I'll move the 2 in front of the 8x, and I'll decrease that to a 1. And then I'll add the derivative of the constant 2. And the constant 2 has a derivative of 0, and then I want to set that equal to 0. I'm setting it equal to 0 because the places where I have a horizontal tangent, the slope is equal to 0. And then I solve. So 4x cubed minus 16x equals 0, and I can factor something out of that. I can factor a 4 and an x out of that expression, leaving me with x squared minus 4. And I can factor that further into x minus 2 and x plus 2. And because that is equal to 0, each of the factored pieces will produce a result for me. So my solutions for x are 0 and 2 and negative 2. And those are the places on my graph where 3 times I have a horizontal tangent of 0. What we've been doing is called the first derivative. That is, Newton called that f prime. Remember that Leibniz called that df over dx. The second derivative, Newton called it double prime, and Leibniz called it d2f. And yes, Leibniz put the 2 between the d and the f, and then he put the 2 after the x. It doesn't mean squared. Okay, it does not mean d squared. It's just his symbol for the second derivative. And then Newton did 3, and Leibniz would do like this. That just means do it again. Find the derivative again. Find the derivative again. Okay? Yeah.
On that last one, where did the 2 go? Not on the last problem. 2 is turned to 0.
The derivative of 2 is 0.
Oh.
Okay? The derivative of 2, remember 2 is a line that has a 0 slope. After that, Newton gave up and he started using, for the fourth derivative, he just switched to the number 4 because it started out as tick marks. The reason is because, remember I told you, what science did Newton really like? He liked physics. And in physics, the first derivative means something, and the second derivative means something, and the third derivative means something. The fourth derivative has no meaning in physics, and so he just really never even bothered working with it, so he just kind of ran out with, and then when they were pointing out with it that there are other derivatives, then he switched over to 4 or 5s, like the numerals. Whatever. All right, so find all the derivatives for this particular function. Now this function has a y, so it would be like this. You would find y prime and see what you get. Okay, so if we go through each term, it'll take us 1 minute. What's the derivative of x to the 4th? 4x, and now a 3. What's the derivative of 2x squared? Okay, that would be 4x to the 1st. What's the derivative of minus 3/4 x? It's just minus 3/4 because that's not a curve piece anymore. That is just a line. And then the derivative of 19? 0. All right. And then y, and you indicate it with a double prime. Okay, what's the derivative of 4x to the 3rd? 12x to the 2nd. What's the derivative of 4x to the 1st? 4. What's the derivative of negative 3/4? 0. And then derivative of 0, 0. And then y3. Derivative of that? 24x. And the derivative of 4 is 0. Okay, now we run into, okay, now he's going to switch. Okay, so then we've got y. You can either do that, if you want, that'll be 24. And then you can do that if you want, and that would be 0. And that's all the derivatives.